Good evening, everybody, and welcome to our third week of Cloud Models, Architecture and Risk Management. You'll be pleased to know that James is back this week so that you'll be able to ask questions, and we've got the technical problems sorted out, and I believe he's got a question lined up already. So James, over to you.
Thanks, Peter. Hi, everyone. Can you hear me?
Yep. I can.
Oh, good. Yeah, there's a question just from Richard before we started tonight, so I thought we'd just start tonight with getting Peter to answer that question for you. Richard's question was, hi Peter, I watched the server cluster video and I didn't think that the video was talking about cloud computing, unless you were talking about the difference between them.
Okay. Right, what we've done with this one, Richard, is I've actually looked at putting a video in about one of the underlying architectures. Now, when we talk about, as we'll talk about this week, the different architectures that we use, one of them is clustering. And this video basically talks to how you cluster host computers together so that you can then run VMs on top of them, and if one host goes down, the VMs can move around and so on. So this is one of the underlying architectures. So from that point of view, it's background information that helps you to understand how this cloud data center is working and how things can move around, and for that matter move from data center to data center as well. So that I'll throw into you as a quick question. If you've got any further questions, Richard, put them on the forum and we'll go into it in much more detail. Any other questions there, James, at this stage?
Yep, that's it for now, thanks.
All right, well, we might get started and have a look at it. So this week what we're looking at is the different architectures. So there's a range of different things we're going to look at, and so this week it's kind of fairly technical, and this is probably as technical as we will get in this particular short course. We're going to look at a number of things like workload distribution, resource pooling, scalability, load balancing, cloud bursting architecture, disk provisioning architecture, and so on. And these are the architectures that underlie the way in which we use the cloud. So what's an architecture? In architecture, formal building type architecture, architects talk about a design pattern, which to them is a formal method of documenting a solution that they have found to a particular design problem, which means that another architect can pick up on that design pattern and solve a similar problem. If we move into the space of software engineering, a design pattern is a general reusable solution to a common recurring problem that exists within a certain context. And so as a developer, I have developed and built any number of different types of modules that I can reuse, right? And this is where this idea of reuse comes. You don't have to reinvent the wheel every time that you want to do something. So in the cloud, we have this same type of thing. There are a number of architectures there, design patterns, if you will, that fit into these two general definitions. And these architectures allow us to have a better understanding of how the cloud itself works and how the architecture of the cloud pulls it all together. But the beautiful thing about knowing these, or knowing a little bit about them, is they start to give us possible solutions to problems that we face. We can start to look at how we're going to solve this particular problem. So we'll start off straight off with the basic one, workload distribution, also known as load balancing, right? And so here what we're looking at is horizontally scaling our resources, right? So we're going to horizontally scale out using a load balancer that has some runtime logic involved in it that distributes the load evenly between the servers. So the idea here is to reduce or is to maximize utilization. We don't want underutilization of one server and overutilization of another. We want to balance it across the server pool, the farm, so that we get an even distribution. So this architecture will apply to any sort of resource that has periodic peaks in usage, right? Now, if you're running an online shop, for example, you might have a peak in usage every time you put up a sale. If you've got a 10% sale for some reason, 10% discount, then you know that you're going to get a peak. You don't know when you're going to get a peak. You know it's going to be in a certain period. So this load balancing architecture can be the start of you being able to scale out so that as more people come onto your shop, the shop front, in order to purchase your goods, you can add more resources there to handle the load. Right? So the idea here is to optimize the resource use. You try to maximize the throughput for the customer. You minimize the response time for the customer. You also avoid overloading any particular single resource by distributing your workload over multiple compute resources. Right? And you'll often use this in conjunction with a whole lot of other different design patterns or architectures. And that's the beauty of that. They're never used in isolation. So you'll use this with resource clusters, where you'll cluster resources together in an active mode. You can use it with the hypervisor, which is used to distribute VM workloads across a cluster. You'll use it with resource replication, so that you can generate new instances of virtual IT resources as the demand goes up. That'll also pull them back as well. It works with a logical network perimeter, so you can set a boundary around this logical network so that it can be distributed correctly. You'll have a cloud usage monitor, which will do the runtime monitoring of your workload and data processing, so that you pay just for what you use. And then you can also have an audit monitor to make sure it monitors the type, the geographical location of resources, in order to fulfill any legal and regulatory compliance requirements. So a simple load balancer will actually act in concert with a whole stack of other things in order to produce what you want. Which leads us to the next one of resource pooling architecture, and this is where we group a bunch of identical IT resources in such a way that the system ensures they remain synchronized. So this pool can be composed of servers, physical or virtual servers, or both for that matter. So you can group your hosts together, the physical hosts, plus the virtual machines, or a combination thereof. You can group pools of storage, pools of CPU, pools of memory, pools of network. And by using these pools, you actually allow the provider to delegate control over the resources of a host or a cluster to a client. Right? And you do this by creating a hierarchy. And there's usually one of two models, the parent and sibling, or parent and child, or the nested pool. So let's have a look at these. So in the parent and sibling, or parent and child pool, you normally build these up from physically grouped IT resources. That is, they're all together in the same data center, rather than using geographically dispersed resources. So you create this pool of resources, a large pool. Then from that, you break that down into a number of smaller pools, the sibling pools. Each sibling pool is then isolated from other siblings in the pool, and you can then delegate control over one of those sibling pools to a consumer. So now he achieves isolation. Right? He's got it now isolated. He's got a set of compute resource in a pool, which is then used by him. So this is how we would do a lot of the IaaS infrastructure. So this is kind of how it looks. So pool A here at the top has been allocated to a cloud consumer. So we've got a couple of other pools, B and C, that are smaller pools taken from the larger pool. So what happens here, we see in pool A, he's got some virtual servers, he's got some CPU resource, some memory, and some network. So he's got this resource there that he can use. Now, this can be broken down into smaller pools, and these other pools can also be allocated. Right? So doing it this way is a better way of doing it, rather than having one large pool, which is in the data center or in the area of geographical area of the cloud, and then allocating straight from that. So you'd set up a series of smaller pools. So if you go down the nested pool model, again, you create the large pool of IT resources. This nested pool is then divided up into smaller pools that have a subset of the resources in the larger pool. And so in here, in the nested pool one, what you do is you will allocate the larger pool to a consumer, and he can then allocate resources to departments in these nested pools. So, a large government organisation, for example, something like, let's pick on the tax office this week. Everybody seems to be picking on the ATO this week, so let's use them as an example. ATO might get a large pool of resources, of compute resources network resources, storage resources, and so on. And then they might have 2 or 3 nested pools under that, and they might give control over one of those nested pools to a business unit within ATO, and the second pool to another business unit, and so on. And so they then use that for their particular tasks, each of those being separated and controlled by a separate part of the same organisation. So also we use these nested pools to provision cloud services that you need to be rapidly instantiated with the same type of IT resources with the same configuration settings. So that's another use for them, that, you know, the rapid instantiation, you've got to scale out quickly, so maybe you put it in a nested pool. So you've got a couple of different uses for this, and please don't think I'm just picking on the ATO, it's just the first one that came to mind tonight. So here's an example. Nested pool A1 and A2 are comprised of the same resources as pool A at the top, but different quantities. And so, as we said, these will be used to provision these cloud resources if they need to be rapidly instantiated, right? Because you're setting up the same type of IT resources, same configuration settings. And so this works really well for the department type structure. So in this particular architecture, we often implement this with a series of other things like resource clusters to put them on, hypervisors, naturally, the logical network perimeter, cloud usage monitor, pay-per-use monitor, remote administration systems, resource management systems, resource replication, audit monitoring, right? There is a pool of other architectural designs that fit into this in order to give you the ability to do what it is you wish to do. We'll talk to this one, James, and then we might stop for some questions. So these three, the load balancing, the resource pools, and now the dynamic scalability, really fit together and give us some good indication of how this works. So dynamic scaling, this is the model, the architectural pattern that uses a set of predefined conditions to trigger dynamic allocation of resources. So this is dictated by runtime usage. So it's you set your thresholds or your trigger points for what is going to happen, and once the demand exceeds an upper threshold or upper trigger point, additional resources are added, right? Now, you might have not just one trigger point, you might have a number of trigger points. And as it goes up and hits another trigger, another threshold, more resources come in. As it continues to rise, another threshold is hit, more resources are added again, and so on. And so you can scale this up in a number of ways. Conversely, as soon as the demand starts to drop, once it starts to drop below those thresholds, then those resources are reclaimed and switched off. Okay, so you're only going to have those dynamic resources running while the runtime usage demands it. As soon as the usage drops back below the threshold, you come back down and the resources are reclaimed and turned off. So as part of this architecture, you have this automatic scaling listener. So you configure this with the upper and lower workload thresholds, and it contains a certain workflow logic to determine the amount of resources that the workload requires, or to subtract them if the demand is dropping. And this is done based on your provisioning contract that you set up with the provider right at the start. So here's how it looks. Dynamic horizontally scaling, first bit. So we've got our cloud consumers here on the left-hand side, and they are sending requests to a cloud service, and they are hitting part of the load balancer, which has got the automatic scaling listener. And so this monitors this cloud service to see if any thresholds are being exceeded. At this stage, nothing's happening, so they go through, they hit the cloud server instances, and they continue to work. Okay, so now as the number of requests start to increase, the workload now starts to exceed the performance threshold. So, we can see there at 4 and 5 there in the middle of the screen that we've now got instances that are overloaded. They can't be met with the current services. So now the policy will now click in and say, is this eligible for scaling? If it is, we'll now start to initiate the scaling process. So this now sends a signal to a resource replication mechanism, which now creates more instances of this particular cloud service. So once that's up and done, then the scaling listener resumes the monitoring and continues to monitor the resources. Now, if the resources continue to stay stable, it leaves it as it is. If the resources or the demand continues to increase, then it will go through the process again, add more. What if the demand starts to drop, then it will correspondingly run the process in reverse and recover some of the dynamic resources that have been added. So there's two other types of scaling in this. We can do dynamic vertical scaling as well, where this is where we'll scale the resources up if there's a need to adjust the processing capacity of a single IT resource, or perhaps scale them down. So, if we've got an overloaded VM, we might dynamically increase the memory or throw in a new CPU core or two in order to assist it. The other type, though, is dynamic relocation, and this is where we literally move the resource to a host with greater capacity. For example, you might have a database running on a tape-based SAN storage device with a 4 gigabit a second I/O, right? And it's being hammered because it's not able to handle the I/O, so it needs greater I/O capability. So we might move that to a disk-based SAN storage, which has got 8 gigabits a second I/O capacity. So now suddenly you've scaled out, you've scaled up, but you've done a dynamic relocation. You've moved it from one host device, a tape-based SAN, to a disk-based SAN, a second host device. Okay, and so that is dynamic relocation. And so the bits that normally, the design patterns that normally go along with dynamic scalability are things like the resource cluster, the hypervisor, the logical network perimeter, the cloud usage monitor, and so on and so on. Okay? And as you start to get used to this, you'll see that these are the normal things that you will be adding in with it all the time. But this is now how it works. So James, I'll stop at this stage and see if anybody's got any questions on the load balancing, the dynamic scalability, and what was the other one we talked about?
Perhaps the parent sibling pool.
The resource pools, yes.
I would say I remembered that, but we have a question about it.
Fair enough.
So we'll start with that one. We've just been asked, what would be a good example of a parent sibling pool?
An EC2 instance in Amazon. Let's say you want to buy some EC2 compute resource in Amazon. They would have, you might buy it, say, for example, out of the Australian data center. So it gives you some EC2 resource. It gives you a series of different levels of resource, compute resource that you can get. So X amount of CPU, X amount of RAM, X amount of storage, and so on. So you pick.
So this is an infrastructure as a service.
This is an infrastructure service. So you would pick the level of CPU, RAM, storage that you require for a particular instance that you want to put up. So behind that, you would then have a resource pool, right? And so what you'd be looking at is you've chosen let's say a small instance. So you might be looking at, say, 4 gig of RAM and 2 CPU cores, and I don't know, maybe 20 gig of storage, just to keep it fairly simple. So that might come out of a particular child resource pool that is set up for small EC2 instances, right? And so that particular resource pool could handle a very large number of small instances. But if you went to the next level, say the medium level, where you might be now looking at, for example, 8 gig of RAM and 4 CPU cores and 40 gig of storage, then suddenly you might move to a different resource pool, which is now set up for medium resource usage. So what you can do with this is you can then, by putting these different child pools in place, you can optimize your resource usage, right? This is the same thing as load balancing in a way, except it's being looked at on an overall basis across the entire data center in order to balance and optimize their load. Does that make sense?
Absolutely. Thanks, Peter. Hopefully it does to you also, Sasadri.
Okay,
good question.
Good.
Just a question from Andrew here. What are some examples of products that provide dynamic scaling?
EC2. it's there. It's built into it if you wish it to happen, right? And it's a matter of configuring it and saying, yes, I want to have dynamic scaling, and as part of that configuring, you can set some parameters around when does it scale, right? So, I mean, one of the things I'll recommend towards the end of this course is that you all go and get yourself a free use on the AWS cluster. You can get a free use on it, and I'll give you the details in the last lecture, and go have a play. Run up a couple of things, scale it out, throw some services at it, see how it works. I mean, you're only using the micro instances, they're very small instances, but at least gives you an idea of precisely how the whole thing works, right? If you're in a hurry, do it tonight. Just look up AWS, just do the Google, and you'll see there is a thing there to have a free trial. Have a play. Does that help? I'm sorry, it's a bit difficult to really talk on that because you've actually got to talk instances of software. But if you want to talk instances of software, consider Gmail, Office 365, Google Docs. All of these are set up in such a way so that as the demand increases, the number of resources are dynamically scaled into it. Okay.
Great, thanks, Peter. Andrew's actually just added an addition to his question, a statement saying he was thinking more of the software, the product by Amazon AWS that they have in place for dynamic scaling.
Oh, okay. I'd have to go back and have a look. I mean, I looked at setting this up some time ago, but I just can't remember exactly what it was. But yeah, I'll go back and have a look and give you the details. I'll throw it in the forum. If Andrew wants to put a question into the forum, I'll put the answer in there for him. Okay.
Cool. Thanks. Hippolito, sorry if I've got that name wrong. Is the dynamic relocation slow? I think to move all data from a server to another must be slow.
I would not expect it to be very fast. On the other hand, it wouldn't be too slow either. I would think you'd be talking a process, depending on the amount of storage you've got involved, a process that might take some minutes, 10 to 15 minutes, depending on what it is. I mean, all bets are off if you've got a petabyte of stuff stored there. That's a discussion to need to have with Amazon or Azure or Google or whoever. But if you've got a few gig of data there, I would suggest that the time would probably be in minutes, maybe 10 or 15 or 20. I honestly don't know. I've not actually run a fair dinkum real life dynamic reallocation, particularly with a bit of data.
Yeah, I guess it's just going to depend on your data.
Exactly.
Cool. Thanks. Just one last question from Richard. Can you only scale hardware properties?
No, I don't know. I suppose I'm not really sure what he means by just hardware properties. Are we talking CPU, RAM, storage?
I'm not sure myself. Richard?
I'm not sure. Maybe we throw that one into the forum, Richard, and we might take that one offline and we can explore it in a lot of detail. I'm just not sure exactly where you're heading with this one.
Sure. Yeah, we'll do it on the forum.
Yeah. Okay. All right. We might get going again then, James, and we'll have a break in another few minutes and ask some more questions.
Great. Thanks for the questions, everyone.
Okay. Let's continue on. Okay, the next one we look at, guys, is elastic resource capacity architecture. So this is what we use for the dynamic provisioning of VMs, virtual machines. So this is a dynamic scaling system for CPU and RAM that allocates or reclaims these resources in response to processing requirements. So effectively, we've been talking with the dynamic scalability of scaling out VMs. So we can also scale out CPU and RAM, because remember, we put CPU and RAM into resource pools, so if we've got them in resource pools, we can play with them. And so they'll be controlled by your VMM, your virtual machine manager. And so, again, you have an automation engine here that will handle these scaling requests, that will work with the listener in order to ensure that once the threshold is reached for RAM, we can add some more RAM or add some more CPU. Okay, so this is the internal version of scaling. Okay, so the way this one works is, we're sending requests through to a cloud service. We've got our scaling listener listening to it, and we have an intelligent automation engine with a script that's deployed with some workflow logic that monitors the resource, that monitors it, right? And it's capable of letting the resource pool know when we've got an allocation request. So we start the requests increase, so the demand goes up. The scaling listener now signals to the automation engine on the right-hand side and says, we need some additional resource, we need to run the script. Okay, the script runs the logic that signals the hypervisor to allocate more resources from the resource pool. And then the hypervisor puts in additional CPU and RAM to the virtual server, and so increases the workload so that it can be handled. And of course, at the same time, once the demand drops off, then the listener will advise the automation engine, which will advise the hypervisor, which will reduce the CPU and the RAM that's been allocated. So just make sure you understand that. That's the version for CPU and RAM, the elastic resource capacity, whereas dynamic scalability is going to add more of the cloud service, which is probably the VM or something like that. It could be an SWS2, but more of the service. Okay, service load balancing. Now, this is a specialized variation of the load balancing architecture, and this is designed for scaling cloud service implementations. So now you use redundant deployments of the cloud service with a load balancing system. And so again, we group these services into a resource pool with a load balancer, either internal or external, and this allows the hosts to balance the load themselves. And so we can have multiple instances of each cloud service implementation be generated in response to fluctuating volumes. Let's have a look at another thing. So if we've got an external load balancer here, so we've got an external load balancer in the cloud, and it does a load balance between three instances of in this case, of the particular cloud service. And so we horizontally scale them by using the load balancer across these three instances in order to provide a balanced load. Okay. The other alternative is we can have an internal load balancer, and this way there the load balancer is built into the service, in this case the service on the left-hand side. So all the requests go to this particular instance of the service, the one with the load balancer. Now, this load balancer has, again, the logic which tells it if the demand increases, I can now send it to the cloud service that's running on virtual server B. Or if it increases again, I can set it to the one running on virtual server C. So another approach to it. Right? Which one's better? Depends on the context. This is going to depend on exactly what you're trying to do and how you're trying to do it. So, but you've got two methods of achieving this. Right? This is the internal one, is probably the one that probably gets used as much as the external. This normally comes out of internally developed applications where probably the load balancer has been built into the service or is attached to it in some way. And so IT departments are probably quite happy with that because they understand how it works. And so by moving it into the cloud, you can then say, okay, well, I want it to hit another redundant copy of the cloud service, right? Or a second or a third redundant copy. Notice they are redundant copies. We're not actually scaling out here. We're bringing up another copy that's already there, right? That's the difference, right? We're bringing up copies that are already there. So they are pre-configured, sitting there, turned off, waiting, right? You bring it up as required. So that's the difference between that one and the external, where you have the external load balancer running and balancing across the three instances of the service at all times. Okay? Make sure you understand the difference. Questions will be asked. And of course, it's often used with resource clustering, hypervisors, cloud usage monitor, pay-per-use monitor, resource replication monitors, and so on. Right? The other design patterns that come into play with this. Now, cloud bursting architecture, this is a dynamic scaling model that bursts out on-premise IT resources into the cloud once you reach a particular threshold. So now, this allows you to have your internal data center, your on-premise IT resources in your own internal data center, and have it then, once demand hits a certain level, hits the threshold, hits the trigger point, you can then move out or scale out to hit the pre-deployed, that is the redundant resources you've put in the cloud that are there, turned off, and just waiting for demand to go up. Right? And so suddenly you've got the other resources come up, you can now work, you can handle the load, and then, you know, at the end of the period as demand drops off, gradually those resources are scaled back and turned off. Now, a classic example for this one is end of financial year processing. Right? You might have a whole series of things happening, a number of databases being worked on, and normally during the year they're not being pushed terribly hard, but come the last couple of months towards the end of the financial year, chaos ensues, demand increases dramatically, particularly in the last couple of weeks of June, and so you might burst out to these other redundant resources in the cloud in order to allow all the processing to be done. So once the processing is finished, then you burst into the on-premise resource, right? And you shut down the cloud. And again, you have this automated scaling listener, part of the load balancing architecture that determines the requests, controls the bursts. So here you've got an automated, I'll get the tongue working yet, an automated listener monitoring the on-premise services for demand for service A, and it then, once it hits a certain threshold, directs it to a cloud service where the customer has a redundant implementation of his service A sitting there, right? And so the listener then manages that, right? And there is a resource replication system we use to keep the two databases then synchronized, because you've got to have that synchronized, and so you synchronize that using a state management data system. So that's the idea of a cloud bursting architecture that allows you to, in some ways, have the best of both worlds. You have your on-premise IT resources working and going. They have to be designed as a proper cloud service though, and then you can scale it out to the cloud and burst out when the demand hits. The next thing that we'll look at, and then we'll have a break again, James, is elastic disk provisioning. Now this is really an interesting one and something that a lot of people don't think about. Normally you go and you'll purchase some S3 storage from Amazon on the basis of, you know, I need a petabyte or 500 terabytes or whatever. And so your storage charge is normally based on the disk capacity that you've ordered rather than the consumption that you're actually using. Because you might say, for example, I've got a big project coming up. I'm going to need 500 terabytes of storage, so I'll order 500 terabytes. And if you do it on a straight fixed out storage allocation, you pay for the 500 terabytes beginning day one, whether you've used it or not. Okay, so the idea of the elastic disk provisioning architecture is you set up a dynamic storage provisioning, so you pay for the exact amount of storage you use, even though you have requested and been allocated more storage. Okay, so this uses a type of thin provisioning technology, and it does this dynamic allocation through the hypervisor. Again, monitored at runtime. And this provides that accurate data for reports and billing. And you want that too, because you want to pay for exactly what you're using rather than this big lump of disk that you think you might need. So here's how it works when it's not deployed. So we've got a server with 3 hard disks, each with a capacity of 150 gig. Okay, so a total provision size 450 gig. So that's our disk space. We have used none of it at this stage. Okay, nothing in the storage, even though we've provisioned the 450 gig. So because it's been allocated and reserved, we will be charged the 450 gig of disk usage at the point of allocation. Okay, so we're paying for it whether we use it or not. Now that is the way a lot of people buy their storage. If, however, you do it with elastic disk provisioning, let's look at exactly the same thing. We get a virtual server, 3 hard drives, capacity of 150 gig each, so 450 gig. We provision that. We set 450 gig as the maximum disk usage allowed for the virtual server, even though we don't actually allocate any physical disk space or reserve it at this stage. Okay, so we haven't installed any software, so even though we've provisioned 450 gig, we've used 0 gigabytes, so allocated is actually 0 gigabytes. So because the allocated disk space is equal to the actual used space, we're not actually charged for disk usage until we start to put some storage there. Then we'll be charged for precisely what is there. So that saves you some money immediately, right? You look at elastic disk provisioning. So we can also do it with a dynamic disk provisioning, right? It's part of the same architecture. So we get a request, we want to provision a new virtual server instance, and so as part of that process we can choose the hard drives as dynamic or thin provisioned disks. So if we use the dynamic disk, right, then it calls this allocation component to create thin disks for the server. Right, this is all done through the hypervisor. The virtual server disks are created and saved in a folder that's near 0 size, right? And the size, naturally, of the folder and files grows as the operating applications are installed and additional files are copied up to the server and so on. And so your pay-per-use monitor tracks that actual dynamically allocated storage. Okay? So that's another way to approach the same problem. So, and mechanisms that follow this, that are part of this, the resource cluster, the hypervisor, the cloud usage monitor, pay-per-use monitor, the resource management system, and resource replication. James, we might stop there for a break and for me to wet the tongue a little bit.
Sure thing. We got a couple of questions that come through and a couple of comments as well, so I'll read out a couple of comments first.
Okay.
Dean has mentioned when you were talking about the possibility of, I think, relocating data rather than scaling horizontally in a certain instance. He says, if you had large volumes of data you want to potentially share between multiple EC2 instances, you'd probably use their new EFS solution and avoid the data copying delays. And that's an interesting point because that's a new feature of Amazon AWS that's coming in soon, I believe, EFS.
Yeah.
I believe it acts a lot like a traditional SAN, which can be accessed with NFS.
Yes, so I believe. I must admit I've read very quickly on it. I haven't had a chance to get into it in any great detail, but it's one of the things that I promised myself to do as soon as I've got a little bit of time and finish doing courses.
Yeah, it'll be interesting to see how it fits in a...
I think it's going to be fascinating. I think this will be a really interesting development, and I'm really looking forward to getting in there and having a play. Any other questions there, James? You still there? It looks like we might have lost James. Okay, I might just keep going. We'll see what happens, but we'll try and catch up then towards the end. So let's move on. Okay, cloud balancing architecture is the next one that we want to look at, and this is again a specialised model that allows you to do the balancing of workloads across multiple clouds. Right? So this now you're normally looking to do this. You want to improve performance and scalability of your resources. or you want to increase the availability and reliability of your IT resources, or perhaps you want to improve load balancing and resource optimization, or you might want to meet the needs of your business continuity plan. So you might balance this across the AWS and the Azure clouds, or maybe AWS, Azure and Google, or Oracle, or IBM, or whatever, or some sort of combination therein. So again, a fairly specialised model, and it's done for one of these particular reasons: performance and scalability, availability, reliability, load balancing and optimization, or BCP, business continuity plans. So it's something to think about. This is based on a combination of a couple of things. You're going to use an automated scaling listener. So this is going to redirect these requests to one of several redundant IT resource implementations. Because remember, you're doing this in different clouds, so you're going to have them pre-set up and redundant. Okay. You have to also be looking at a failover system to ensure that if you have redundant resources, that they are actually capable of a cross-cloud failover. So if it fails in the AWS cloud, you've got to be able to bring it up straight away in Azure or Google or IBM or whichever other cloud that you're using it in. IT resource failures are announced so that the listener can avoid the inadvertent routing of requests to an unavailable resource. The last thing you want to do is push resources, try to push resources to AWS if it's gone down for some reason. You want to push them off to other resources that are still up. So this is basically what it would look like. You'd have a scaling listener controlling the balancing process, and it would route consumer requests to redundant implementations across multiple clouds. Right? And so if you had a failure, you've got a failover system there that instills this resiliency by allowing that to, if one cloud disappears or suddenly has a problem, to move to another cloud. The next one we want to look at is hypervisor clustering. Okay, so again, this is coming right down to a very technical architectural, physical layer, because the hypervisor is actually sitting on the physical host. So these are the software that's responsible for creating and hosting these multiple virtual machines. So if you lose a hypervisor on a host, it's going to cascade to all of its VMs. Okay, so if you're going to cluster hypervisors, right, what you're talking about is creating high availability clusters. So you'll have a group of hosts that are clustered together, so that the virtual machines created by a hypervisor on one host can be moved to another host. So, for example, at work we run a couple of Hyper-V clusters. We run one in our data center at Bathurst, one in our data center in Sydney. So if I have, let's say, I've got 10 hosts in a cluster, and let's say one host is having some issues. So I can manually, or I can leave the VMM, the virtual machine manager, to organize it, to move all of the VMs off that particular host. I can take it down, I can repair it or replace it, and then bring it back up again, and the VMM, the virtual machine manager, will reallocate the VMs back across all 10 hosts. So this is the architecture that underlies most of the clouds, right? The clouds, the providers buy, straight black box hardware. There's nothing. It's just straight hardware. There's nothing sensible about it. Well, it is sensible. It's just all standardized componentry. The idea is if a service starts to create problems, they're not going to try and repair it. They take it out and they replace it. So it's just pulled out, a new one pushed in, bang. So it's offline for a few minutes until it's replaced. The server that's pulled out is taken away. It's examined. If it can be repaired, it's repaired. If not, it's a commodity thing. It can be sent back or repaired or perhaps done something else with. Right? But the whole idea is it's replaced and done very, very quickly. Okay, so that's what underlies the whole idea of the the cloud. And this is what most of us in our data centers are starting to move to, no matter whether you're using Hyper-V or VMware or Zen or anything, the Oracle version, anything like that. Providing you've got some sort of hypervisor running on your hosts, you can move your VMs around that cluster of hosts that you create. So that's the same kind of architecture that underpins everything in the cloud. So here we go here. If we haven't got clustering deployed, in case number one there, a physical server is running a hypervisor, has 2 virtual servers up. If we turn off the physical server, or let's say somebody trips over the power cord and pops it, then the minute the server goes down, the hypervisor dies and the 2 virtual servers drop. Okay, so everything fails. However, if we move to a clustering type system where now we cluster these 2 physical servers together, they both have hypervisors, they both have virtual servers. However, if physical server A fails, the host fails for some reason, then the virtual server is moved to the new host. Right? So it just migrates across to physical server B. It has a hypervisor, it's part of the cluster, it can go live over there until such stage as server A is brought back online. And of course the hypervisor would dynamically scale the resources available to all of the VMs so that all the resources are shared. So here we might have hypervisors stored on 3 physical servers, okay, each running a hypervisor, and each server then creates a number of VMs. Right, so now in this particular instance we've got at number 3 there at the top a shared cloud storage device, or it could be an on-premise SAN, which contains all the configuration files, and this is put in such a place that all the hypervisors or all the VMs can access it. So, and underneath it there is a central Vim or a VMM, depending on whose hypervisor you're used to using, that the virtual machine manager or the virtual infrastructure manager that controls the cluster. Okay. So in here, these servers exchange heartbeat messages according to a schedule, and that lets everybody know, including the Vim or the VMM, that the cluster is up and running and that everything is working correctly. However, if server B fails or becomes unavailable, so this would normally mean that the virtual server C above it would drop. So now here in this instance what we've found is that we're no longer, A and C are no longer getting a heartbeat from B, right? So what happens is the Vim says, okay, physical server C now will be the new host, and so it will, having assessed the capacity, make the call, move the VMC to physical server C, right? So it's live migrated. It's not turned off and turned back on again. It is moved live. And so it may be necessary to restart. It depends on, again, on the server and the context and what you're running on it and so on. But effectively, normal operations can run. Using our instance, again, we do live migrations all the time, and we don't require restarts. It just happens. I mean, from a client point of view, out in the workplace, nobody knows that we've migrated a server, even if they're on it, talking to it. So if it's one of the SharePoint web front ends, for example, if there's something wrong with the physical server that one of the web front ends is on, we might migrate that WFE to a different host completely, and yet the people on it will notice no difference. Okay, guys, there we are. That's it for tonight. We've got some reading for you. It's a really, well, I thought it was a really interesting one anyway. An architectural pattern language. If architectural patterns are not your thing, and I can't understand why they wouldn't be, but if they're not your thing, don't bother. However, do watch the videos, because there's one there on dynamically provisioning virtual machines, there's another one on server clustering, and there's a third one on cloud bursting for elastic applications. And this one I found fascinating, because this shows how an application can burst out of a private cloud to a public cloud as demand increases. And that's one of the things that I'd really like you to think about, because that's one of the really interesting and really good use cases that we have for the cloud in relation to the on-premise IT. And of course, the weekly test is there as well. So, James, are you up and running at this stage?
I'm back.
Excellent.
Sorry about that, guys. I lost sound for some reason, which has happened to a couple of other people tonight. Sorry about that.
Okay, do we have any questions?
Yep, there's some questions here. The first question was by Craig, who has asked, to simplify his question, he's asked, how does CSU utilize cloud computing to run the online short courses? Which is one that I would probably initially start to answer myself,
okay,
given that I'm intimately familiar with it. So this, for the short courses, there's probably 2 or 3 major systems in place. The main one that you guys will know of is the learn.itmasters.edu.au website, which is a learning management system. It runs on a piece of software called Moodle. It's actually sitting on Amazon AWS. It's on an EC2 server. Richard Lane has just said Interact, which is Blackboard, which is another LMS, which is used internally at CSU for the non-free short courses. An interesting answer to how is cloud computing used for the short courses is that we're using it kind of ham-fistedly at the moment, which is funny because Peter's teaching all this great stuff about cloud, but actually that learn.itmasters site it's in a cold failover sort of situation at present. There's one EC2 instance that it's running on. There's another one in another region that's there as a cold failover that certainly can be switched to manually if anything goes wrong. It's not load balanced. It's not hot failover. And so actually in answer to another question previously that we've already touched upon is, do you scale up or do you scale out? Do you scale horizontally or vertically? If presently we need to add extra resources to that site, we need to essentially add CPU and RAM. That'd be right, Peter?
Yeah.
Which, according to a lot of proponents of the horizontal scaling methods of cloud computing, is kind of ham-fisted, and it certainly isn't. It's not truly elastic, I think. Would that be the term? That's
correct. I mean, it's the process that's normally used in on-premise IT data centers, where if your server is running a bit sluggishly, the normal sysadmin responses will throw some more RAM at it, or maybe another CPU core or 2, and perhaps a bit of extra storage, and we'll incrementally play with it till we adjust it. So it's kind of load balancing by sysadmin. There is no real automation behind it, and it's more by guess and by feel and by what we've done in the past rather than putting proper automation in place. What we have to move to, and this is one of the problems I'm finding at my workplace at the moment, is trying to convince sysadmins that there is another way. And as an old sysadmin, I know the way in which they're kind of resisting that particular change, because that's the way they've always done it. Yeah, I can relate.
Absolutely, yeah, and it's a tough new concept to get used to. It's a whole extra layer of sort of to work with that load balancer and essentially multiple servers doing the same thing. How do you make sure that they're both doing the same thing and such?
Yeah,
there's certainly more complexity there.
Yeah, I think what it boils down to is running a trial instance and seeing how it works, figuring out for yourself just how this thing actually plays in the workplace, and then trusting the automation that you've set up. I mean, we all write scripts and we trust them they're going to do what we want to do, right? This is just a much bigger script.
Absolutely. It's the hands are. swaying a bit more back to a developer sort of thing, isn't it? Yeah.
Very much so. I mean, your sysadmin tasks are really starting to become developer tasks. You are becoming an application producer. I'll use producer rather than developer because a developer actually creates the application, but a producer in the context of, say, a film producer provides it to an audience, right? And that's
Absolutely.
really the method and the way in which we're starting to move. So a sysadmin is probably become a system producer or perhaps a system director. Choose your own metaphor here, but I'll claim it first. Quote me if you want.
So yeah, if anyone
Yeah, let's start a forum post on this.
hammering out.
I can talk on this one for years.
Yeah, well, it's largely it seems to be the core of the cloud movement in a lot. Well, it's one of the big cores of it. So it's good to have a solid example to go by. Thanks for the question, Craig.
Yeah, great question.
And so certainly the plan for the future is to when I have time for this particular project is to set it up so that it horizontally scales, uses a load balancer. And yeah, so in the meantime, I hope no one takes that information and tries to DOS our server while people are doing exams, please. That'd be nice. And another follow-up question that was asked was, so what instance of EC2 are we using for that Moodle server? Is it micro, medium, large? Which, as you were saying, Peter, dictates the amount of CPUs and the amount of RAM, 2 gig or 4 gig of RAM. Presently, it's a medium-sized instance. It used to be a small, an M3.small, I think it's called, and it was increased to medium when we had a short course with, I think, 6,000 on it at once, and we decided that it wasn't quite going to cut it.
Yeah.
And so that was vertically scaled reasonably easily, but not ideal. We got another question here. Does elastic disk provisioning allow storage to shrink as data storage is reduced?
Well, it's what you're really concerned about with elastic disk provisioning is you're paying exactly for what you use. If you're reducing the amount of storage you're using, you're going to pay less for it, which I suppose is the aim. You still have a certain amount of overall allocation. If we use our example, 450 gig is what we've overall allocated. We might be using, let's say, 20 gig of it. We might throw some more data in and run it up to, say, 200 gig, and then having finished the processing, pull the data back out and run it back down to, say, a final figure of, say, about 40 or 45. When you're finished, you're paying for 45. You've still got 450 allocated, so you can expand at each stage to 450, but you're only paying for actually what you've got there. And that's really the critical thing with that. You've got an overdraft, if you will, of storage. You can have so much storage, and you only pay for what the bit that you're going to use.
Yep. Michael just piped up and said it's now called DevOps, where you were talking about being a producer. I think would DevOps be the...
DevOps is kind of where it's going, although DevOps kind of actually does, it's kind of, I suppose, agile development on steroids with sysadmin thrown in. I was trying to leave the development bit out of it and really just talk about the sysadmin side. So, you've produced an application, or somebody's produced an application. They've developed it, you want to produce it for your particular crew, right? So DevOps does, I'm not entirely in favour of the term DevOps in this instance. It's close to it, but probably not too close, because it's still got that development aspect in it, which, development really talks to the application and doing things in the application, whereas I'm doing things to the application as opposed to being in it. It's a bit of a fine difference, but does that make sense from my point of view? Again, let's take this out in the forum and argue it out.
Yeah, I think so. there's a lot we could say about that on the forum. It'd be
Yeah.
great. Actually, on that note, a few people posted links that looked pretty good tonight. Sorry, I didn't sort of repost them in the chat because I didn't want
No, that's fair enough.
to, I guess, have people clicking off onto other things right now. But if you guys want to post them on the forum, I think that'd be really great.
Yep.
We just got a question from Avanish here saying, there's a lot of talk with regards to AWS. How about Azure and Google Cloud? And another question from someone else just saying, is there a checklist? That was from Avanish as well, actually saying, is there a checklist or a good way for choosing between the big players?
Well, I suppose I'm only using AWS as an example, which I said right at the start. I use them as an example because they have probably the best and certainly most accessible documentation. So, and I was originally looking to try and use the Azure stuff, but trying to find their documentation is just, dear, painful. However, the AWS stuff is dead set easy. It's really, really well written. And so it just fell out naturally that it's probably, well, it is the biggest cloud service running at the moment. So, yeah, I just ran with that for no particular reason other than the resources were extremely easy to get a hold of, right, and really well written. So on that basis, I chose AWS. I certainly have a very good relationship with Microsoft and Azure, and I do use Azure and that myself. So, and that's why I keep talking about them and Google and IBM and Rackspace from time to time and so on. So I'm fairly agnostic about them. It's just that, as I said at the start, I'm going to use AWS as the example and the exemplar in this particular course, mainly because of their documentation. Okay. So a checklist for choosing the big players, oh, gee, that's a call. It depends on what you want to do. You know, if it's just general compute, you probably can't go past the top three, you know, AWS, Azure, Google. And then you've got a few others coming into play from there. If it's something specialist you want to do, you know, if you're looking for a specialised set of software, then there's a number of little cloud providers that running, you know, software like, for example, Salesforce, if you're looking for a particular CRM solution, or Xero, if you're looking for an accounting solution. These are all, you know, running as SaaS services from various different clouds. And in fact, a lot of them, like Xero, are cloud balanced. That is, they're balanced across a number of clouds in order to provide that resiliency and that availability. So, you know, if one cloud's having access problems, we can load balance it straight off to another one. So, yeah.
Yeah, I think
difficult to answer that one.
It's going to come down to a lot of personal preference. I think
and it is
the big ones do the
preference.
very similar things.
The critical thing here is do your research. You have to go and do the research, right? No way around that one. Got to do the research.
A couple of comments. Richard has said Azure integrates well with Visual Studio, so if you're a purely Microsoft shop, it might not be a bad choice. Benjamin has said Google Cloud is limited with architecture to Linux workloads only.
Right.
That is or was the case, probably still is.
I mean, I'm looking at using the Azure Cloud for a burst-out architecture using System Center. Naturally, you know, I run a System Center implementation in Azure, and I can use that with my internal System Center implementation to do a burst-out if I need to. And so that, you know, when I discussed that with our CIO and IMB, Information Management Board, they were kind of interested in that because that solves a number of problems from us from a number of points of view. You know, demand, business continuity, resource usage, upgrades. You know, there's any number of different solutions that sort of pop out of that one. So, you know, yeah, look, as I said, I'm agnostic towards the cloud. I'll pick the one that always give me the best results. Simple as that.
Certainly. When you burst out to the cloud with your System Center, is that all offline before it goes up there?
Yeah, well, you've got to have a redundant system center implementation up there to start with. So
Yeah, and it's got to be in
we're
sync.
still in the process of arguing that one out, what we're going to do and how we're going to do it, whether we're going to do it. But I've certainly put together a proposal and an architecture on that, which says this is how I think we should do it, and this is how I think these are the problems I think it will solve, and we are exploring further. Let's leave it at that. Okay.
Thanks. That's great. It's a good example. Andrew has just asked, 10 minutes ago, sorry, Andrew. I'm curious to how machines migrate in a failover without the user even having to log on to a new virtual instance.
Yeah, it's fabulous. It just, I didn't believe it would work myself, but it does work. And the that dynamically provisioning virtual machines one will give you some idea. There is another one I saw which I couldn't find. I'll go look for it again, which was a good, quick little YouTube video. It was only 4 or 5 minutes, but it showed how it did a live migration. So I'll see if I can find that again, and I'll post that onto the forum as soon as I find it.
Awesome, thanks. I'll just do one more for tonight, and we'll probably wrap up. We've gone a few minutes over time. Michael's just asked, are cloud providers susceptible to DDoS attacks?
Everybody's susceptible to DDoS. I mean, one of the things that cloud providers do is allow you to approach it from a slightly different direction. So they're probably a little more resilient than most people. So it would really depend on what you're trying to do, I think. But yeah, it's. I mean, if somebody really wants to do DDoS you, they will get you if you're really a target. So it's a matter of making the best provision you can about that, and that's one of the things we'll start to look at next week in the lecture on security. And in the meantime, if I find any more information on that, I'll put it up for you.
Cool. Thanks, Peter.
Not a problem.
So everyone, that weekly test is open now up at learn.itmasters.edu.au. You can sit it any time you want, as usual, up until the end of the course.
I've just been making notes about what I've got to go find. Okay, righto guys, thank you for attending tonight. I think James have already put the lecture notes up, and if not, they'll be up shortly, or the recording of the video will be up probably tomorrow, James, I'd say.
Yep, that'll be up probably, about midday tomorrow.
Yep.
And the readings for next week are up, so you can get onto them as soon as they've done the ones for this week.
Mm-hmm. And I think that was about it, unless there's anything else you've got.
Nope, I think that's about it.
All right. Okay. Thanks very much, guys, for attending. I hope you've got something out of it, and we'll see you all next week. If you have any more questions, put them on the forum. I will be on the forum tomorrow morning, and we'll start chasing them down for you. Okay. Have a great night. Thanks, guys.